now we're at that point here to understand a little more clearly now. And we're ready to make our way into formally defining what it means by being a Riemann sum right here. All right, so I need to have you look back at the video, so maybe rewind the video possibly to look back at the activities I was doing with the x square function from between 0 and 1, and then from any of the example we have done just now. Okay, but mainly the idea now, and I still have that on my calculator screen here as well. So, all right, so back on our computer screen here. So we only need to say with the 4 subintervals, and then we will get a lot of good ideas out of that already. All right, so this is what we did. The whole idea now is that one interval that we're doing, and even let me roll back to the beginning problem that I promoted, that's where we start from 0 to 1 here. Okay, so from 0 to 1, the total interval here, okay, we broke that down into 4 subintervals. That's the first activity that we did right there. All right, so now the general idea now is that you have a function. And this is, now I'm having my final opportunity to continue with that generality I brought up earlier. That, so we have a function. Our first activity was the x square function, but the idea now is that it's some function being continuous function. And of course defined in the certain interval that we are working with. So the interval here is from a to b. And so now inside of that interval, we're looking at the promoting problem. Now I have to be clear, the promoting problem here is that we want to estimate, we want to find the area inside of that part, trapped between the curve of the function and the x-axis, and between from a to b, our starting point of the interval to the end of the interval. Okay, and so this is what we did right here. We broke that down into subintervals, and that's what we did. So I even did this earlier. I call this interval number 1, interval number 2, interval number 3, number 4, and if I even broke it down into more intervals, and 1, 2, 3, 4, 5. But no matter how many intervals I want to break it down, but it's all being limited in this overall interval from a to b right there. And so that's why you have seen earlier, and I trigger your thinking a little bit earlier, that the more subintervals we're attempting, then think about how it changed our intervals here. Each of the subintervals width right there. Okay, but so now the idea of instead finding the exact area, that's the work right there. We couldn't do that yet because we didn't have any definite formula. So we did that by, so for now we are already through with that step. We're breaking down into subintervals in equal widths. Okay, so the width here is always b minus a over n. That's something else I also need to remind anyone again. So each of the width here is b minus a, the total length divided by the number of subintervals we're working with. So for now, just think about 4 of them. Okay, and then from that point right here, see, if we pick any interval, let's say pick interval 2 right here, then between the interval, then we have our choice to pick. A point either the left or on the right hand side. Okay, and so generally speaking, at this point, allow me to introduce this. The left endpoint in any interval. So any of the interval here, let's say at this particular interval, I'm going to call that the interval 2. So the left endpoint for interval 2, I call it x2, but with a superscript L right here. So on interval 2, that's the left endpoint that we chose. Okay, and so generally the idea is this: we picked the left endpoint, okay, in that interval 2, and then we plug that into the function, substitute that into the function. That's to get heights of the rectangle, because eventually we're going to draw the rectangle. So see, if we're doing that, then it's going to give us the height is determined by this. And so from that, we're going to draw over and get our rectangle. All right. And so in that way, that's the height for rectangle 2. And then we multiply with the delta x, the width. So that's for one rectangle, and specifically rectangle number 2 right now. So that generality there was for all other subintervals. So at any I subinterval. So so now that was specifically at second rectangle number 2. So now I'm going to talk at I'm talking about generally at ith subinterval. And specifically, let's look at the left endpoint for now. Then this is what we did. We picked the left endpoint. So at the ith interval, it's x sub I. That's what I'm doing. And then the left endpoint right there. And then substitute that into the function and multiply that with the width that was previously calculated. That gives me the area of that gives me the area of the ith rectangle. Okay, so rectangle 2, that's x2 on the left. Okay, and substitute into the function and multiply with the dx. Okay, and so, but then that's not all of the work we did. This is only for one rectangle. This is, see, that's why I'm saying at some ith subinterval, right? We created the rectangle with the area being done as indicated here. And so the generality that in the end, the work that we did there, now I have to really explain right here. So we have to start out all the way from first, this is now number 1, first rectangle, but picked left endpoint, substituted that into the function to find the height, and then multiply with delta x. That was area for the first rectangle. Then we accumulated that. That's why I'm having an adding. So we accumulated that with the height for a second, or for a rectangle number 2. That's why x2 right here, but on the left endpoint. Okay. So the height here, see, rectangle number 2, left endpoint being substituted into the value, into the function to find the height, and multiply again with the width. This is area for rectangle 2. This is area for rectangle 1, and then so on and so on. And so the function at x3, this is the value in the third interval on the left endpoint. Okay, that's what the superscript L is for. So this is the height of the third rectangle, multiply with the width again. And see, in a general setting like this, we can go to as many n as we want. That's why I'm leaving dots right there. Okay, but we're doing all the way to the last one. So if we have n subinterval, we go x sub n. Left endpoint on the n interval. That's what this x sub n superscript L is for. Okay, and times delta x. So this is a general setup. But see, this right here is what we've now formally referred to that as the Riemann sum L sub n. Okay, or so a little more formally, you are welcome to use this long version, or there's a more condensed version, which is, because it's a sum. It's a sum. So usually when you arrive at a calculus class, then your mathematical majority is higher now. It's higher. So you are ready to accept, to take the symbol. It's a summation. We sum all of the, you see, generally at any of these area right here, the formulation is that it's the left endpoint at any ith interval, generally at any ith interval, substituted into the function. That's what the f at x sub I to L right there, superscript L, multiply with the delta x. Okay, and then we're summing all of those little areas. In areas, I keep using the term area just to have you have that envision, that visualization about every single thing we do in here it came from that original promotion right there. But that is formally now we define that. Okay, so now as a definition, now as a formal definition, this setup right here, or in this setup right here, is now called is called, and it's just a generality we drew out from throughout doing our activity. And so it's now called the left Riemann sum. All right, it's called the left Riemann sum. And I will come back and point out more details about this. But right now, as the way how it looks, it's just simply starting with the interval. It's all about we start with an interval. Okay? And you don't even have to think of that as area. We will get to that and even clear with that idea with just simply you got a function and then and a given interval. And so at least in that given interval, now we define the operation, the kind of work, we define the kind of work that we break the interval into equal width subintervals. Okay, and there could be just 4 here, or there could be a lot more. Okay, but then each of the width now is the delta x. We can calculate that value by b minus a over n. Okay, and then so on each particular ith subinterval, we formulate the following. We formulate the idea now is that, so if you don't, I start recommending to think of this as just simply the function value at the left endpoint on any general ith interval right here, any general ith interval, instead of seeing that permanently as an area. I don't want anyone to get your mind completely stuck with the idea of area. Okay, because at some point later on, Riemann sum and areas will at some point depart from each other. Okay, but so for now, all I want you to understand is we define the work, we define that operation by, hey, at any general interval, we pick the left endpoint, substitute that left endpoint into the function. And so we get a value, and that's why as a picture, the value is the height of the graph at that left endpoint. Okay, but then having the height right there, I call it the height because I want you to associate with the picture, but it's just simply the function output at the left endpoint on the given ith interval. And then we multiply with the delta x. And then we're not doing only for one interval, we're doing for all intervals, for all subintervals we've had. And so in that way, and then once we've had all of those products right there, from all of those products, nail down, we're going to sum up all of those products. That's what the Riemann sum is. Okay, and then in specifically each of the products here, that function output here came out from left endpoint on your particular subinterval there. So that's why we call this, it's the left Riemann sum. Okay, so in that way, same way, I'm going to roll back to my board. And now, instead of doing, we also did this back in our earlier activity, back on the x square function. Same way that we already have broken down our interval into subintervals, equal widths, of course. Okay, and so now this is what I'm doing. Say, for example, third interval, or we can still stay with second interval, but for third interval, instead of using left endpoint, I'm going to use a right endpoint. So I call that a little different symbol right here. So on the third interval, I pick the left endpoint. That's why it's the x value on the right endpoint of the interval number 3. Okay, substitute that right endpoint into the functions, and so we get something like this. We get something like this, interval number 3, but use the right endpoint. I'll get something like this. Okay, that gives me the height, and then from there, I'm going to create my rectangle as that. All right, so that's the rectangle. So on rectangle number 3 right here, I pick the right endpoint, substitute that into the function to get an output, and that output there is multiplied with, or being taken as a product with delta x, calculated previously here. Okay, and then we're going to do the same for the other rectangle. So say back to number 2, now instead of picking the left endpoint, I'm picking the right endpoint, so right endpoint goes as high as right here, and drawing over, that's my other rectangle. Okay, and so that means generality, as a generality here, then at any ith subinterval, then we're going to, instead of picking the left endpoint, we pick the right endpoint. Okay, we pick the right endpoint on that, And so at the ith interval or on the ith interval, we pick the right endpoint, okay, and substitute that into our function to get an output. And that output, we usually envision that or visualize that as the function's height at that point x sub I on the right endpoint. But then we multiply that output with the width dx right there. So now moving over to my other board, we're not only doing that for one particular interval, but we're doing that for all of them. So now allow me again to come up with that general formulation here. I first tried to retain some of the stuff we've had, but I decided to erase everything. So here, think about specifically at interval number 1. Then the right endpoint now is going to be notated as x sub 1 for interval 1, but right endpoint on first interval. Substitute that into the function to get some kind of output, to get an output value, and multiply that with delta x. That's what we did. Just the work we did here, but for first interval. And then as I said earlier, we're not only doing that for one interval, but we're doing that for all intervals. If we break it down into like 100 intervals, we have to do from x1 all the way to x100. And so f of x2, that's for interval number 2, that's the right endpoint on interval number 2. That's x value specifically gets substituted into the function and multiplied with the difference dx, delta x right there. And we're going to start accumulating those. And again, I'm going to repeat that for the third interval. Okay, so x3 superscript or multiply with delta x. And I'm going to keep adding more until I reach the last one, the nth interval of mine. When I reach the nth interval, then it's going to be f of x sub n to the r. So the n here is a little bit different with the I. I should have also mentioned that when we were doing the ln earlier. But it just means this is really our last one on the list. If we break it down into n sub intervals, then x sub n here or x sub n or is the last right endpoint on our last interval. Okay, and then we multiply that with delta x. So the n here is different with the I. The I here was just to indicate that when we're at any interval before the end, or it could also be any interval from the beginning to the end. That's what the I is. But now this x of n here is just for the last one. So that sum right there, we define that to be Rn. That's what it is. Okay, and so now alternatively, we have the summation notation. This Rn is defined as the, so basically I want to, my viewers, my students to start seeing this simply as an operation, a work that we define. Start departing away from areas. Any of this is just an output at the right endpoint of the function in that interval 1. Multiply with delta x, already previously calculated. Then this is function output at the right endpoint on interval 2. Multiply with the delta x, and so on and so on, and we sum it up from the beginning to the end. And now, that's why in that way I have a summation notation. So if we're summing all the I from 1 to n right here. Each of the index right here, we're looking at taking the right endpoint on any of the current ones, okay, substituting that into the function and multiply that with the delta x right there. Okay, and so summing it all up, it's just what that sum is, but instead of the lengthy descriptions, we're going to write in the shorter descriptions. I recommend that know both of these, be flexible with any of these. Okay, and so this is now called so that sum, like the sum defined like that, is called the right Riemann sum. All right, the sum like that is called the right Riemann sum, like that. And so now, I even have to push your thinking, because Rn, Ln is just one of the two cases, one of the two specific cases of the more general version of the Riemann sum. We haven't reached to the main general understanding of the Riemann sum yet. So what exactly is the Riemann sum? So now allow me to erase this. Okay. So now let me just completely speak on behalf of any general ith subinterval. So at any general I subinterval, then we can have the following. So in any I subinterval, we can either have, and as I already mentioned, it's just a choice right there. On the ith interval, we can look at the left endpoint, okay, or the right endpoint, because these are both two different components of your ith interval. Any interval has to have a left endpoint and a right endpoint, so any one of these belong to your ith subinterval, or it's an interval, it's a point of that interval, a point of that interval. Okay, either the left endpoint or the right endpoint. It's a point of that interval. And so now I'm going to generally define the following. I'm going to how about call that just a C point. Okay, so it leads me, so knowing that, you know, either being a left endpoint or a right endpoint, just simply a point, just a point of that interval. And so it led me, or it leads me to this following understanding. I'm going to call it, it's a C point. C sub I point. That means it's just simply be a point. It can either be the left endpoint, or the C sub I can also be the right endpoint. Okay. It's only a choice between these. That's why I'm saying, you know, we choose that, and maybe that's the reason why I call it C. It's a choice, but that choice can be the left endpoint or the right endpoint. But when we stick with one, we stay with the rest. Okay. Once we stick with one, and with the rest of all the other intervals, you have to stick with that same point right there. Okay. So here's the actual general Riemann sum right here. So the whole idea of the Riemann sum is that instead of focusing specifically on left endpoint or right endpoint, now I can just say on each interval, I can just pick a point of that, a point I, a CI point. I'm a little bit ahead of myself. This is C1. It could be left, it could be right here. Okay, but once it's left, it's left for the rest of it. Once it's the right endpoint, it's the right endpoint for the rest of all these guys right here. But it's a point of the first interval. It's a point of the first interval, 1. And so in that way, this x2 or here, that's a little too specific. Generally, we can regard to this as a point C2. Left endpoint or right endpoint is just a chosen point, okay, of subinterval 2, okay. But like I said, if we already decided to stay with left endpoint, and all of these guys are all left endpoints. If we chose a right endpoint, and all of these guys are right endpoints, okay. And so now I can modify this version, okay, as a C3, okay. And so same way here, I can modify this final one, this last one for our last interval as a C. And they're all lowercase. That's what I meant to write with that. And so this right here is a sum. It's a sum. And so, but I can't call it L, because L is more specific as using the left endpoint. I can't call that R, because it's a little bit too specific as it's already specifically used as the right endpoint. So here I'm just going to call it, it's some kind of sum, okay, by summing up n terms. Okay, it's a sum by summing up n terms. Each term here is done by picking a point of the interval either on the left or on the right. Substitute that into the function and multiply with the delta x. Same thing here for second interval. Pick a point, and now whatever you chose here, we chose the same one there. Okay, but it's the same agreement with that. But pick that point, substitute into the function, and evaluate and get some output. And so we're summing up all of these terms from beginning to the end. We have this is now, or in summation notation. In summation notation, it's a summation f ci multiply with delta x, okay, and summing all from the first term to the nth term right there. Yes, we call it S of n. And I have to admit at this point, this S of n right here is actually just my own term. Believe me, I've taught calculus for years, and I've seen many different textbooks using different the symbols here. So some textbook might agree with my symbol, some textbooks use other symbols right here, but in the end it's just a sum. Okay, and we created the sum this way. Now the L sub n symbol, the R sub n symbol, I agree with many other textbook authors because that's probably the best way. But when it comes to the general version that I'm introducing here, some other textbook use the symbols here. So that's the part where, be flexible with me on this. So I'm using S of n. Textbooks will talk about this kind of work as well, but may use different symbols here. That's what I'm trying to point out right there. And so now this definition, this sum right here is called, okay, it's just a definition of the kind of work we're doing here. And when we do that kind of work, we call that, we're taking the Riemann sum. Okay, so this is called the general Riemann sum. Okay, and just the Riemann sum. Forget about the word general. I write it here, but I'll put it in parentheses. Okay, the main term here, because you can skip the word general. This is just called the Riemann sum. All right, so that's formally what the Riemann sum is. Okay. All right, so now after having a careful discussion and explanation of the formal definition of what it means by a specific left Riemann sum or a specifically right Riemann sum, and then we led our way into a general definition of a Riemann sum in general, then we are ready for doing an example over here. So let me clear out my board. And so now keep in mind that at this point I start wanting my viewers, my students who study this video lesson with me to start seeing the Riemann sum as just simply a sum that we define. So once we see that instruction, we work that way through the problem. And you will understand what I mean by as we get into this example here. So now I'm going to call it example 2. All right, so on example 2 right here, we are given a function being a continuous function. How about x cubed? Okay, and this function, and that's all we are having for a function like this. And I want to, let's evaluate. So this time, instead of saying approximate, we actually evaluate, okay, part A, or 4. Let's evaluate or 4 on this interval from 0 to 1. Notice in my instruction of the example here, I did not use any word area at all. I did not get to that point of completely making you depart from, making my viewers, my students to depart from areas and Riemann sum yet. But it will come after we finish with this problem. So the point of this example here is that I want you to simply take the problem here solely or entirely as a problem where we're summing up. That's all. We're just summing up. Forget about areas. Forget about areas. So we have an interval from 0 to 1. Our function this time, at this point I'm seriously getting tired of my x squared function. So let's switch over to x cubed. Okay? And then when you are more mature in math, and you can do the same work here on other functions as well. The interval is from 0 to 1. I want to find our, so let's learn to speak it out a little bit, okay? This is, we want to find the Riemann sum, the right Riemann sum, using 4 sub-rectangles, using 4 sub-intervals to be precise, on that interval specifically given here. And as it said here, it's a right Riemann sum. That means on each of the sub-intervals here, I'm going to pick the right endpoint to get my function evaluation. Okay, so here we go. So let's look at a couple prepping steps right here. Delta x equals, see, and at this point we're so clear that it's completely legal that we're using equal widths. So 1 is the final point, minus 0 is the beginning point of our total interval divided by 4. We want 4 subintervals. So this is 1/4. Or in decimals, if in case anyone is more familiar with decimal, 0.25. Okay, and so now I'm going to use my next board. And let me spend some time erasing it. And now again, for this particular example, if you're working along the way with me, I highly recommend it's entirely a math problem, but we're not worrying about the area picture or anything like that. Okay, so again, it's a good habit that we're doing this. The interval from 0 to 1 on the line of numbers. Okay, so on the line of numbers, there's our interval from 0 to 1. I'm going to break it down to 4 subintervals as instructed. As instructed. Okay, and so now in that way, this is 1/4 because, or 0.25. This is 1/2 or 0.5. This is 3/4 or 0.75. Okay, so in that way, this is how we're doing the OR4 here. OR4 will be done by, it's a sum, but for the first term of the sum, here's what we're doing. It says OR, that means now look right, the first term of the sum comes out from the first interval. Interval 1 is here. Okay, and see, I don't even need to worry about what graph is the x cubed function. Interval 1, interval 2, interval 3, and interval 4 right there. Okay, so on the first interval, the instruction of the problem says I want the right endpoint. So on the first interval here, the right endpoint is this guy, 1/4. So now I'm going to have to take the right endpoint, substitute that into the function, and then I'm going to multiply with the delta x that we have calculated previously, 1/4. Okay, let me quickly swing back to the other board to convince you. This is our delta x value. Okay, and now, see, that's the setup, the general setup for how we're doing that. Okay, and I completely ignore, I don't even want to mention about the graph of the x cubed function or whatever. If you know it's good for you, it's not needed for our problem here. Okay, next term. So now we're done. And don't even think about areas of rectangle or anything like that. That's not what we need. Now we're moving on to the second subintervals. The second subinterval here is okay, right endpoint again. So right endpoint on the second subinterval is 1/2. So f at 1/2. See, I take the right endpoint. The rule for all the terms here is that at each term I'm going to take the right endpoint on the interval correspondingly. Right endpoint, substitute that into the function, get some kind of output eventually, and multiply that with the delta x that we have calculated previously. That's what we're doing. Okay, and now I'm going to add that to the next one. Okay, so on the third interval, because we're done with second term, on the third term, that means we're at the third interval. So 1, 2, 3, right endpoint is here. So f at 3/4. I'm going to 3/4 there. I'm going to multiply with 1/4 being our delta x. Okay, and I'm going to add with my last term. My last term comes out from the fourth interval. So right endpoint of the fourth interval is 1. So now f of 1 times 1/4. Okay, see how easy we can follow that setup right there. And of course, if you are a little more experienced with running the summation symbol, I'm not against at all that you are using that. But in the end, when we really are adding it, it's all going to be like this. So from 1 to 4, okay, all of the f of some c sub I right here, right? And multiply with the 1/4. And then in the end, we're still going to have to spend some time breaking down the c sub I right here. Okay? All right. And so I'm not going to specifically going in that route. So I'm going to stick with this long sum right here. But you see the general idea. So now, throughout all 4 terms here. We're not doing an area problem. Keep that in mind. Okay? They're all having common factor here. We have our legitimate rights. Pull that out in front. Now in parentheses here or in brackets here, see, function output for 1/4 is going to be 1/4 cubed this time because the function given here is a cubic x cubed function. That's why I'm doing that. Now plus f at 1/2 will be 1/2 cube. Should have done that. F of 3/4 is going to be 3/4 cube. Okay, and f at the last one here in our work is going to be 1 cube, and then we put that in brackets. Okay, and so that's how we're coming closer and keep getting closer to getting our final answer of R4. And I'm talking about R4. I'm not saying anything at all about area. All right, so my final calculation show R4 equals 0.390625. That is our answer for this particular problem. Calculating, evaluate the actual value of R4 right there. All right, and so now we are ready to make our way out to part B of the example. So it's just another question right here. We're still staying with the same function f of x given here to be x cubed, and we want to evaluate. But here in this case, I'm going to change to a different question. All right, so how about for part B here, let's look at, we want to evaluate L4. So learn to speak the name of these symbols now. So L4, the capital L4 means it's the left Riemann sum using 4 subintervals. And so we already clearly defined a Riemann sum at this point is not only an area. I mean, the area is the best place where we apply the Riemann sum idea, but the Riemann sum on its own is just simply an operation. We define the operation that, hey, we break it down, we break our interval down, so here's the interval. We want to find L4 on the interval from 0 to 1 again. And so back to what I was in the middle of saying, we want to break this interval into 4 subintervals, and then from there on each one of the interval, on each subintervals, we're going to pick the left endpoint, and then we're going to produce a sum. We're going to produce the sums, etc., etc. And so I'm going to start making my way out to the other board so that we can get started on that. All right, so since we're looking at the exact same interval and with the exact same number of partition points, the exact same number of subintervals being required here in the problem, and so it's good that I can still retain this exact chart here. So there's our interval from 0 to 1. I broke that down according to part A of the example we were now doing. Then we broke that down into 4 subintervals, and I had the red numerical labels here in red ink over here. And so each of the space here, maybe I should always get anyone into a good routine in case the problem here was the only one problem and as an independent problem itself. So delta x is always the final point of our interval given minus the beginning point or the initial point divided by the number of subintervals we want. And so our delta x for this problem here, finding L4, is going to be 1/4 or a 0.25. And that is the reason why now I can legally use the chart here that I have made for part A of the example. So that's exact same chart here. I broke my interval down into 4 subintervals, so consequently each of my delta x here has to be a 0.25 or a 1/4 in space. And so now in that way, consequently, it's easy now enough to see how these partition points are being calculated here. So 0, and the first one here is a 1/4. The next one is has to be a 1/2. So, and values go increasingly up to 1. All right, so for now, for the L4 that we're specifically looking for, the left Riemann sum with 4 subintervals. So now in the first interval, so just like that, the Riemann sum now just tells us that, hey, in each interval, for now, as for the first interval, I'm going to pick the point as designated here be the left. So I'm going to pick 0, the left endpoint, and substitute that into the function. And that's an operation. It's a work that we do, not necessarily to find area. And I will get back and emphasize this with a better example later on. But now, once we've had that output, we will multiply with our dx here, in this case being a 1/4. Okay, that's how much that space here in each of these subintervals. And now I'm gonna, so that takes care of the work that I did on my first interval. Then the second interval, now once again for the second interval, left endpoint is at 1/4. So I'm gonna substitute 1/4, the left endpoint of our second interval, into the function. And I'm gonna multiply with the width again. The width of the interval is 1/4. Okay, and then for the third interval, interval number 3 now, left endpoint is 1/2. And so now 1/2 is substituted into the function. And then same way with how we define a Riemann sum here, I'm going to multiply that with the delta x quantity, which is permanently a 1/4. And then we're going to add that to the last, for the last interval, left endpoint is a 3/4. And I'm going to, again, substitute this value, this left endpoint, into the function. And then multiply that function's output with the interval with delta x equals 1/4. And so now we already, and see, when we were looking at this problem here, I moved on, I went over these problems. I was going over these problems completely without the graph, without switching back and forth from the graph and showing the graph, because I want viewers, I want my students to learn this problem in this current example entirely as an evaluation problem that we just carry through the process, the operation here, and we got an answer. And it's not necessarily an area problem. Okay, and so now as a further step right here, f at 0, our function was an x cubed. So with our function being an x cubed right here, then so now I can get back to my function. So x cubed here is going to give me 0 cubed times a 1/4. And I should also continue the same practice I've been doing. I recognized a common factor of 1/4 in each of our terms here. So why don't we factor it out? So maybe I'm going to write it down in a little bit in the lower line right here. So 1/4 is being written as a common factor. And then first term in my parentheses, instead of writing f of 0, I no longer need to do that. Now we can just go straight forward into 0 cubed as the value being substituted into our x cubed function. Then I'm going to add to the next term. The next term now, after pulling out the common factor of 1/4, now we're looking at 1/4 cubed. Then the third term is going to be 1/2 cubed. And the last term is now going to be a 3/4 cube. All right. So that's the setup that's ready for getting the final answer. So I'm now again going to quickly step back to my computer to get some calculated results here. All right. So my final answer now shows left Riemann sum with 4 subintervals is finally calculated as 0.140625. Okay, and one more time, let me double check to see whether I've had the correct answer written down. And yes, that was the value. Okay, and nowhere throughout this problem and the earlier problem in part A that I mentioned about an area, the answer here is good that we use that to approximate an area, but it's not necessarily always an area. It doesn't always mean an area. Okay, and so now I'm going to clear out my board again. And same problem. same function. I want to evaluate in part C here of our example. How about we're going to evaluate R4 again? Okay, so we're back to doing R4. So we're going to be doing similar work with what we've done in part A. But this is now, I'm going to switch to a different interval. How about -1 to 0? Okay, and the process some of the process will be similar to what we've done in part A because it's R4. And again, what is this? Right Riemann sum. It's a Riemann sum that we want to particularly pick the right endpoint on each of the interval, on each of the subintervals throughout this total interval here. And we're using 4 subintervals in this particular given total interval. Okay, and so again, first step, as a common habit and a good common practice for anyone into doing any of these Riemann sum problems, we're going to nail down the delta x value. So delta x in our case here, final value of our total interval is going to be 0. So 0 minus -1. That's the beginning point of our interval. Now I'm dividing that by 4. So that gives me a total of 1/4 or a 0.25. Okay, and so now I'm going to advance to my other board, clear out the board, and then I am going to have to reconstruct this chart indicating all of the partition points because my beginning point is no longer 0. In this problem, my beginning point of the interval is at -1, and 0 is supposedly here at the end of the interval, of the total interval. All right. And so whatever can still be retained, I already had it up here without erasing it. And so now we can look at -1 being the beginning of our interval, and then 0 is here. So now with the amount of space being a 1/4 for each of these little sub-intervals here, and of course, forgive me again that I'm completely off scale. I'm a human being. There's no way I can compete with the machine in terms of precision. But so if we're having a -1 and we add with a 1/4 into that, then here we're looking at a -3/4. Okay, and a -3/4 is a -0.75. Okay, and then if we're adding another 1/4 space to the right hand side, we're looking at a -1/2, which is in decimal -0.5. Okay, and so you stay with whichever the convention that you're more comfortable with. You can either go with the decimals or a fraction, and then with another 1/4 here, you're going to look at a -1/4. So what I said meant was if we add another 1/4 space to that -1/2, we ended up with that partition point being a -1/4 or a -0.25. And here, if we're adding that final space being a 1/4 to this current -1/4, we're ending up with that final point of our interval being a 0. And so now, after getting that chart there with all the partition points being successfully nailed down and labeled, and I still have my sub-intervals labels here. So we're ready for R4. So R4 in this case is going to be, again, the setup comes out as following. For first interval, I'm going to pick the right endpoint and substitute that into the function. So that's a process. I want anyone following this example to see this problem as a process, and we just follow through the process. We get some kind of calculated value nailed down. So -3/4 is the right endpoint on the first interval. Okay, and so -3/4 substituted into the function, and I'm going to multiply with the delta x, and our delta x is 1/4 in this case. Okay, now I'm going to move on to second subinterval, subinterval number 2. Right endpoint is a -1/2. That gets substituted into the function. So -1/2 is substituted into the function, and we're going to multiply that function outputs currently for second interval on the right endpoint. We are multiplying that with 1/4, the delta x again. Okay, and moving on to the third. Now we move on to the third interval. Then right endpoint is -1/4. So -1/4 is substituted into the function. I'm going to multiply that with our delta x that we have found. And I still have a little bit space now. So right endpoint for my last interval, or interval number 4 now, is 0. So f of 0 times the delta x 1/4. And so I'm I have to write that a little squeezy into the other board of mine right there. But that's now the complete setup for our R4 calculation. In this particular case where we shifted the interval to a different interval, -1 to 0. And I said shift, the reason here is that we still stay with the same function, the same x cubed function, but we changed to a different interval. Okay, and so let's continue further. And again, at this point, I can start speeding up the process now a little bit. 1/4 is a recognized common factor, so we can algebraically pull it out in front. Okay, and then now left behind in the total parentheses here, I'm going to look at function output for f at -3/4. And so it's a -3/4 in parentheses cubed plus, and now a -1/2 in parentheses cubed. That's what this is for. And our function, again, as a reminder, it's a cubic function. Plus, now the next one here is going to be a -1/4 cubed. And the last one here is a 0 cubed. All right, so that's the calculation setup. Before I tell the actual answer, I want any one of you who are viewing this video, go ahead and get your own answer. And I want you to have a moment to think about this answer before I write down the answer I have. And then we're going to talk about it all together. All right, so now I have an answer. The answer this time for R4 in this interval is going to be negative. And let me spell it out loud, or how about on my writing on the board here, I'm going to write the sign as in red ink. So how about negative, and the actual magnitude here is 0.140625 here. So the answer is a negative. Okay, the answer is a negative. But then at least this is the final answer to our problem. The final answer to our problem for this particular question, with our given function here being namely f of x equals x cubed. I was asked, or I was instructed in this question to find the right Riemann sum using 4 subintervals on this particular given interval here. And so the work here consequently came out. The work consequently came out being negative, and negative what, 0.140625. Okay, and so now I have to say, as far as being able to perform a Riemann sum problem, anyone watching this video at this point, being through with me on 3 different problems here, I believe you are fluent. As far as getting the answer down, we're fluent. But now, before I completely close down this example, let me bring that down and emphasize what I have been saying in the last maybe the 10 or 20 minutes lately. See, I keep emphasizing lately that a Riemann sum is not necessarily an area. Okay, and so here, this is what it is. So area, I have to be clear, area is the best place where we can use a Riemann sum to apply and find an approximate for area. But the Riemann sum itself, so if we're now looking at the definition a little more closely, then the Riemann sum itself is not necessarily an area. Okay, so see, back to that the general definition of a Riemann sum, of a general Riemann sum that I mentioned earlier. So all we need is, on any interval, on any ith interval, we can either take a right endpoint or a left endpoint. So I came to that ultimate general version where I call it as a chosen point in any ith interval, and substitute that into our function. See, so everything I'm doing here is simply an operation. We chose, we picked a point specifically of that specific interval where we're at, and we substitute that chosen point into the function. Okay, so that's why it's an operation. And then after that, the operation goes further. We multiply that with the known, the found, the calculated delta x. And then we're summing up all of these terms, because we're not only having one subintervals, we're having as many intervals as indicated here, as many subintervals as indicated in the problem. And so we're summing up all the way from the first rectangle, and that's what our I1, I equals 1 to I equals n is for. So if we have n subintervals as requested, see, that's what the symbol S of n is for. We want to create a sum with n subintervals that came out from n subintervals. And so on each interval, this is what we do. This is what we're doing to each interval, and then we're summing all of these little calculations from the beginning to the end, from the first subintervals to the last subintervals, okay, to the end subintervals. So that's purely and entirely and only what it is for being a Riemann sum. And so now the reason I keep convincing anyone viewing this video to start departing away from the fact that a Riemann sum has to be an area, nope, it's not, because here's why. So now look back at the result. In our example 2, part C right here, it's still here on the board. The answer was negative. The answer was negative, and I wrote that sign clearly in red ink right here. The answer was negative. So here's the reason. If we keep thinking, if we keep tying the Riemann sum to an area and only accept a Riemann sum as an area, then we will be stuck with the idea that area has to always be a positive value. We will be stuck with that permanently. But nope, in this case, since we purposely define this Riemann sum here generally only as an operation where we're summing up a function output, right endpoint or left endpoint as a choice, a function output at a chosen point on an interval, on a specific interval, then multiply with a delta x. So the function output itself could be a negative, okay? Because some function could be, who knows, some function has a certain area or a certain zone that falls below the x-axis. So these function outputs here in this case are actually the negative vertical line right here, the vertical side that sink below the x-axis, okay? And so that's actually what happened in this particular part C of our current example right here, because these function outputs here, a lot of these were negative. See, when we tear it down to these calculations, that one was negative. That one was also another negative, okay? And any one of you watching this video can always pause the video and verify my calculation. That should be a negative here. That cubic, another negative. So it makes things more negative. It makes things even more negative, and that one is a 0. Okay, and graphically speaking, let me switch over to the graph right here. Here's our famous f of x equals x cubed. Okay, and so the interval of interest, the interval that we're interested in is here, from -1 to 0. And so the two tick marks that just now being displayed here, these are these 2 points are to indicate we're looking at the interval from -1 to 0. And so in that interval, we are breaking it down to 4 subintervals. So now I'm going to put in the partition points right there. So we got 1, 2, 3, and 4 subintervals. And now with these subintervals, see, if we really have to visualize the picture here, then this is what the right Riemann sum looks like as a picture. There we go. So now all of the rectangles, yes, they're still rectangle, but now in the way how I'm seeing it, the rectangles sink, all of those rectangles sink below the x-axis. And so consequently, they result in, this is negative heights, another negative height, another negative height, and this height here is a 0 height right here. Okay, and so summing up all of the negative heights. So area cannot be negative. That's why I want anyone, when you start learning formally about a Riemann sum that I'm writing on the board here, when we learn formally about a Riemann sum, then Riemann sum on its own is not necessarily an area, and so we don't have to permanently tie a Riemann sum to an area, because if we're only strictly thinking of a Riemann sum as an area, then all areas have to be positive. That's the way it is. We cannot have a negative area, okay? Because it's an actual physical shape. So for something physical, we can't have a negative area. But now Riemann sum on its own simply is an operation. So operation can be negative, can be positive. And so in that way, among all of these the function outputs at our chosen point on each subinterval, some of these outputs could be negative. Okay, and so that's why in this case now, a Riemann sum in general doesn't necessarily have to be always positive and doesn't always represent an area. It's just on its own and on its truest meaning. It's just an operation that we define here. Okay, and so now that's the whole intention. So hopefully after my explanation here, you're really gonna have to depart away from taking the Riemann sum only as an area. Okay, the Riemann sum is the best tool for us to approximate and find area, but the Riemann sum on its own is not necessarily an area. Okay. All right. So now we're good with this example. And at the end of this example, that's where we have finished looking at all the details about the Riemann sum. All right, and so now at this point, I believe that anyone viewing and learning from this lecture, this concept of the Riemann sum has seen enough and has had enough idea about what a Riemann sum is. And so now in this continuation of the lecture, allow me to extend the idea of using the Riemann sum into a slightly different direction, but completely a creative idea right there, and that will expand your understanding of how we can effectively use the Riemann sum idea. Okay, so let's recap a couple ideas. And so throughout the whole problem, I motivated the situation. I promoted the problem with the problem as following. We have a function f of x equals x squared, and now for start, how about we want to inside the interval window from 0 to 1, and then so the x squared function in this window is going to be just the piece of the curve like that, the piece of the parabola like that. So that's the graph for f of x equals x squared. And then precisely on the graph right here, it is going to be this graph. Okay, and so the interval from 0 to 1 is here. And that's our interval that's slightly up here, that was slightly up here at the bottom of on the line right here. And I purposely, again, I've been hiding away all the numerical labels so that we can just mainly get the idea without worrying about values and all that. Okay, and so now with the Riemann sum using the right endpoint, then we were able to, and let's say for now, for simplicity, let's choose 4 subintervals. So we break the interval into 4 subintervals. So from 0 to 1, that's the window right there, and then we break the interval into 4 subintervals. So the total window here, the total lengthy interval is broken into 4 subintervals. And then we're still gonna take that idea of using equal width. That's just making life simpler for us. So in that way, each of the little space here, as we have already learned up to this point, is going to be a delta x. So any of this here is in delta x. Okay, and so needless to say, delta x here is simply the value, the final point minus the beginning point of our interval, and divided by the number of desired subintervals here. And so in that way, particularly in this problem, we're looking at delta x. Each one of our space here, little subspace right here, is 1 minus 0, the ending minus the beginning, divided by 4 subintervals that we desire. And so here we're looking at the delta x is equally spaced, being a 1/4 in each of the spaces here. Okay, and so now if we were doing, allow me to recreate the picture on the other board like that. So if we were going with the right endpoint, so the idea was with 4 subintervals from 0 to 1 with 4 subintervals, then on each interval we're going to purposely pick the right endpoint. So the first interval here, I'm going to pick the right endpoint, and from there I produce, and that was the idea of the right endpoint, the Riemann sum with the right endpoint, and symbolically we notated that the R4. So on the first interval, on each interval, we're going to purposely pick the right endpoint. So for the interval number 1, sub-interval number 1, I picked the right endpoint, and there we substitute that into the function, and we create the height of our rectangle. Okay, and I hope I don't have to go back into ultra details. That means we just reversing the whole video lecture so far. Second interval, second sub-interval, I'm gonna again choose. So the rule here is to choose the right endpoint on each sub-interval. And so in that third interval, I'm gonna choose the right endpoint here. Okay, and the right endpoint is responsible for the height of our rectangle in that designated sub-interval. And for the last interval, the right endpoint is here, and then into the graph itself, it produced this height right here. So that was R4, and we were accumulating this. So we have seen all that idea back in the earlier part of the video lecture. And similar picture. On the same graph, I can also, and in the same window from 0 to 1, breaking it down, after breaking it down to 4, and as a decision, after breaking it down to 4 sub-intervals equal width, even though I tried my best to make equal width. Interval number 1, interval number 2, number 3, number 4 right here. But on each interval here, we also had a choice to pick the left endpoint. So for the first interval, the left endpoint is here. And so that's responsible for a rectangle at height 0, because substituting the left endpoint on this particular interval, that's x equals 0 right here. Substituting that into our function x squared is going to give me that height being 0 for the first rectangle. And then for the second rectangle, or in the second interval, sub-interval, then we choose the left endpoint. And so here, the left endpoint on each interval now is responsible for the height of our rectangle. So our rectangle here has the height, or assumes the height of whatever comes out from the left endpoint. Okay, and then for third sub-interval, again we pick the left endpoint on the third sub-interval, and then from there, substituting that into the function we create, and that left endpoint is responsible for our height of the rectangle over that individual rectangle, over that individual sub-interval. And the same with the fourth interval, we again picked the left endpoint, and the left endpoint was responsible for getting the height of our, so the ending point of the interval is here at 1. Okay, at 1, I should have made that value bigger so that people can see these are just the number of the rectangle. But here is the actual value on our total interval. And so now left endpoint in the fourth interval is responsible for this height. And so now in this way we have seen that using left endpoint, and this notationally it was symbolically it was L4, it was the Riemann sum, but where each interval is where we chose the left endpoint on each interval to calculate our height of each rectangle. Okay, and so I keep emphasizing that term, we chose. And so generally we already came to that idea that about, let me put that on the beginning board. So we came to the idea that any Riemann sum generally at any number of desired subintervals is basically a chosen point in any ith interval substituted into the function to get the height, and then that height there is to multiply with the width, because the delta x will appear, the delta x right into the picture appears to be the width of each of our rectangles in each of the subintervals here. And so in that way, at any general height with a chosen point in the interval, and remember, now many textbooks, I have to also clarify, many textbooks use this, in any interval x, in any I interval, they choose an x sub star, x superstar right there. But I decide to use this. See, it means the same thing with many standard textbooks. It's just indicating that we picked a chosen point. So I use C here stand for chosen. So we picked a point that's chosen inside of any of our ith interval, and then that point, chosen point, is substituted into the function to come out with a height, and then the height is multiplied with the width, and that gives us the area of one rectangle, And then the whole idea of the Riemann sum is simply just that after we getting, and so throughout n sub-intervals, we are going to expect n little rectangles. And so we can sum up this product between height and width on any rectangle, summing from first rectangle to the last rectangle. And that's the idea of the Riemann sum in general. And so I purposely emphasize on that idea that this CI point right here is a point chosen. So earlier in the lecture, I went with left endpoint and right endpoint. It was a choice to use the left endpoint in the interval, to use the right endpoint in the interval. Okay? And so now what's the extended idea that I'm about to introduce in this video lecture, in this particular part of the video lecture? So we had our right to choose the left endpoint and right endpoint, and specifically and generally the Riemann sum was stating that we don't have to specifically go with any left endpoint or right endpoint. We can just generally choose any x value inside an interval, inside any interval. And so in that way, the extended idea here is that in each subinterval, we can also pick the midpoint. So again, I should have also labeled with red ink in my earlier picture as well. And now I'm going to quickly erase this. So the red ink here is the first interval, second interval, third interval, and fourth interval. Okay? But now in each of the interval here, I am going to pick the midpoint. So of course, in my current drawing on the board here, I'm just a human being. I'm not going to compete with machine in order to, pick the precise midpoint. But I will demonstrate good enough with the idea. So midpoint is there. Okay? And that midpoint I am going to substitute into the function, and it will give me a height. Okay? And then, just like that, I'm going to pick again the midpoint in the second interval. So now, just specifically being the midpoint, allow me within my video lecture here to use a symbol. So how about, it's an x value. Okay? In interval number 1, so it's x1, but how about a capital M as a superscript? Just like I've used that earlier in each of the problem about the left endpoint and the right endpoint. In this interval, how about let me now fix that with red ink right here. In the first interval, right endpoint is here, and so earlier in the video lecture I introduced x1 at the right endpoint, meaning subscript here is it's the first interval. It's an x value in the first interval, but being precisely the right endpoint. And so similarly, this point right here for the second interval, second subinterval, I call that it's second interval, but right endpoint. Okay, the x value that's in the second interval, second subinterval, and at the right endpoint. Okay, and then that one here specifically, okay, was the x value, and x value specifically in the fourth interval, and chosen to be the right endpoint. Okay, so that's a superscript right arrow, and that last point also happened to be the last value of the ending value of our overall interval. It happens on the fourth interval. It's part of the fourth interval, so it's x4, but the right endpoint. Okay, so and I use x of I with the superscript L right there to indicate a left endpoint in any designated I interval. And so in that way, so now it's just between me and my own students or viewers who follow with my lessons right here, then that first point being the midpoint of the first interval, so allow me to use a notation x sub 1 with the superscript M right there. And so needless to say, this point right here, that point there is x2. It's an x value in the second interval, but being the midpoint specifically. It's a chosen point, okay? It's a point we chose. But then once we substitute that value into the function, then we can create a height for our function. Because in the end, it's an x value. Substituting that x value into our function, graphically speaking, it will create for us a height. And so there's our rectangle, the height, and multiply with the space dx, the width dx, I mean delta x here. It's going to give me an xm right there. Okay, and so just like that, this is x3, that's x, midpoint in third interval, okay, x3, x sub 3 midpoint. And so substituting that into the function and along with the delta x given, okay, I have created a third rectangle, okay. And so now the midpoint in my fourth interval is right here. So that's the extended idea. So instead of picking the left endpoint or right endpoint on any of our intervals, on any of our sub-intervals, I picked the midpoint this time instead, okay? And that gives, it's another perfect approximation. So the midpoint here in the fourth interval give me a height as such that you can see in the picture. And so now I can draw the rectangle over, okay? So that's how I create. So in this way, ladies and gentlemen, allow me to introduce what we're doing here. It's a Riemann sum. Okay, it's a Riemann sum. But now, as an extended idea about using left endpoint or right endpoint, or it's just a new direction, a different direction, I call that, this is the midpoint. Okay, and in this specific situation right here, we are going with 4 sub-interval. So I'm calling this, it's the M4. So capital M stands for the midpoint rule. So now here we can call that midpoint midpoint rule. All right. So in addition to left end point, right end point, here we got midpoint rule right there. And so symbolically it's capital M, and here in this specific problem so far we are using 4 sub-rectangles, 4 sub-intervals. And so now the M4 here we're looking at is generally, see, at any of our midpoint, at any of our sub-intervals here, we're looking at x sub I, and I shouldn't put this summation notation too soon, but we pick the midpoint. And then that midpoint gets evaluated into the function, okay? Gets evaluated into the function, and then that gives us a height. So if that was x2m, then that is the height right here. The height is this height in specific. This height, I'm trying to make the arrow pointing to that height right here. That height is the function at x sub 2, the midpoint in the midpoint, the function at the midpoint in the second interval. That's what the 2 is. And so, and then that height the height in each sub-interval is multiplied with the width delta x, okay? I might have accidentally say dx sometimes, but I meant so far it's delta x. And then we're summing up all of these rectangle areas from the first rectangle and in our specific problem to the fourth rectangle, okay? And so that's a generalization of the problem so far. So now let's head on the other board and let's see how the calculation will come out. For us this time using the right endpoint rule right here. Okay, so we know that in this board right here, we know that each of our delta x value, each of our space in the picture is a 1/4. Okay. And then A is 0, 1, B is 1. That's the ending of the total interval. So now, first, and again, just like how I have been recommending, the total interval from 0 to 1, I highly recommend try to sketch down your interval with the proper partition. And so these are the partition points because we break it down into 4 sub-intervals. So this first partition point is a 1/4. This next one right here, or numerically it's a 0.25. This middle one right here, really at the middle of the interval, is a 1/2. Or a 0.5 in decimal. And this is a 3/4 or a 0.75. So these are the partition points that break our interval. Those are the boundaries between each sub-intervals. But so now our actual point now is in the first sub-interval. And again, allow me to use red ink. In the first sub-interval. Okay, in the first sub-interval. That's what the red ink is for. our point has to be exactly midway or midpoint between 0 and 1/4. So that point has to be here, and numerically it's 1/8, or in decimal point 125. Okay, so that's 1/8. And then the next midpoint for interval number 2, for subinterval number 2, has to be, so now that's the midpoint right there. Okay, and the halfway. So in case anyone's still unsure about how to find a midpoint between any 2 points algebraically on a line of number like this, then you can just take the left end point being 1/4 plus the right end point being a 1/2. And I should have written that 1/2. I don't understand why I had it as a 1/5. So 1/4 plus a 1/2 right here. Okay, and that will, and then divide that by 2. That will land us into the exact value of the midpoint. Okay, so that's the midpoint is the average value between these two, left point and right end point right there. Okay, and so in that way, I'm looking at 3/8. Okay, and so this point right here is 3/8. Okay, and then so on and so on. And that point here for the third interval. Okay, and that's going to be 5/8 here. And then it just now fraction works a little bit better for me, so I just write these in fraction. But you are more than welcome to label these with the decimal expressions as well. So fourth interval here we're looking at 7/8 right here. So those are the midpoints. Okay, and that I wrote them, and hopefully it's clear enough from some distance from the camera, in front of the camera. So now laying it down, in the first subinterval at that midpoint being a 1/8, we are substituting that into the function value, and then that gives us the height. We're now multiplying with the width 1/4, and that gives us the area of the first rectangle. So quickly, as a demonstration, the area of the first rectangle is here. Okay, the area of the first rectangle is here. All right, and so now, then we need to accumulate. We need to look over to the second rectangle, the second subinterval. And so the height of the rectangle over that subinterval is going to be determined by the function value at the chosen point 3/8. So I'm substituting 3/8 into the function to obtain the height. And then that height is going to be multiplied again with the space delta x equals 1/4. And we're adding that in. Okay? Because we're accumulating, it's a sum now. So at this point, anyone is well aware that it's all about we're summing up little areas to get a bigger approximate that's hopefully close enough to the actual area in our the work. And so in the next one right here, third rectangle is here. We're going to obtain the height of the rectangle over that third interval by substituting that midpoint in the third rectangle, in the third interval. So 5/8 substituted into the function. So f at 5/8, and I'm going to multiply that with 1/4 again as the width delta x. And the last one here, of course, the function value at 7/8. That gives us the height, and I'm multiplying that with 1/4 to complete our area of the rectangle. And now we're summing that up, and all of that there, the final answer will be regarded as M4. Okay, that's going to be M4. And so now, in actual calculation, I'm going to write down one more step right here. So M4 as an actual calculation, it's going to be a 1/8 r squared, because our function is square. Our f of x is x squared, as a quick recall from the earlier information that I had on the other board right there. So f at 1/8 means we have 1/8 squared times 1/4. And then after setting up all of these calculation steps right here, I'm going to quickly step away for a calculation. And so now in the next one here, I'm looking at 3/8 squared times 1/4. And for my third rectangle, I'm looking at the height being 5/8 squared, or the square of 5/8 times with the width 1/4. And for my last rectangle, it is going to be, the height is determined to be the square of 7/8. 7/8, the square of 7/8 times the width 1/4. So now it is clear that we're summing up the areas of 4 sub-rectangles. And now I am quickly going to step out. I'm going to step over to my computer station to graph an actual calculated value for this. All right, and so the calculation on my calculator gave me 0.328125. All right, and so this is the sum. This is the Riemann sum using midpoint rule with 4 subintervals, with 4 required or desired subintervals. Okay, and so that's what we have found here. It's M4. Okay, and so now let me do a quick demonstration with the graphical display on the computer screen right here so that you can have a better visual sense of that. All right, so again, this is our graph for the famous function f of x equals x squared right here. All right, so f of x equals x squared, and now according to the activity that we just did, and I want the interval here is from 0 to 1. So let me now show the interval in our problem. So here's 0 right at the origin, and on the x-axis, this is 1. And again, as I have explained so many times, allow me to hide the numerical label of these values right here. But that's, I can tell you, it's 0, and this point right here is 1. Okay, and so now I'm going to show the partitions. We want 4 equal width subintervals, and so with the desired number of subintervals being 4, here's our partition. So that's the first subintervals. This is number 2, this is subinterval number 3, and this is subinterval number 4 over here. Okay, and so now here's the demonstration. Here's the picture, the actual nice and precise picture that Desmo created for me with the midpoint Riemann sum over here. All right, so there we go. These are the midpoint Riemann sum. So you can see that the idea remains the same. In each subinterval, in each of our subintervals, we have a rectangle over. The width of each rectangle is our famous delta x right here. But now the height, you can see that the height here, now let me really make it clear by making some adjustment to my Desmo's graphing calculator here. But now allow me to show, so these are the midpoints. So the first midpoint here happened at 1/8 based on our partitioned charts earlier, and so now the second interval, subinterval, then the midpoint happened at 3/8, which is this dotted black line right here, and then the third one is here, and the fourth one is here. Okay, so and that's the picture of our, that's the picture to represent our right midpoint rule using 4 subintervals. Okay, to approximates the area inside the curve x squared and the x-axis in between 0 and 1. Okay, and so now back into the problem. Again, I have to emphasize, anytime we have come out with the answer to a Riemann sum, that is only an approximate. Again, making it it's as a connection back to what I have brought up way in the beginning of our lecture, then our main aim is to find the area. And I also said now when we were still on the computer screen, our main aim is to find the area between the curve x squared and the x-axis. Okay, because that was a very beginning problem that motivated into all of these inventions of the Riemann sums and all that. And then we are restricted in between a window from 0 to 1. So area between the curve, the x-axis, and a lot of time famously people call that it's the area under the curve. People always assume that any curve is above the x-axis, which is okay, but more generally it's the area between the curve and the x-axis. Okay, and then restricted inside of a given interval like that. That's the basic idea. But then using the left endpoint or the right endpoint or the midpoint or any general Riemann sum is only going to give us an approximate, okay? It's not the exact area, because you can see that right here we got some white space right there, and again on my picture, okay, the green area, the green's area accumulated here is the area that came out from M4 here, from summing up 4 sub-rectangles using midpoint rule, Riemann sum with midpoint rule over here. But in the end, there are still some white spaces, and you can still see some white spaces, and some green area stays above the curve right there. So in the end, what I want to emphasize now is that this answer is only the answer to M4, the Riemann sum with midpoint rule at 4 subintervals. Okay, but it's not our area. So the ultimate, if this was a problem asking us to find the area, the only way, and just like how we have done that with left endpoint and right endpoint, the only way to make a conclusion here is the area is only approximated, the area between the curve given in this activity and the x-axis and inside the interval from 0 to 1. That area is only, can be approximated by this value, 0.328125, 3.328125. That's all we can conclude. We are not saying that this value for M4 is the area, because you have already seen that there's still some amount of being off. There's some white areas being left out, and there's some green area being above the curves, according to the picture I put on the computer screen. Okay. And so the reason I said that earlier, because now it's time to know that anyway. So just like how we were doing that with the left endpoint and the right endpoint, now the more intervals, the more subintervals we desire, the better approximates we are going to achieve. So here in this particular starting out activity right here, I was going with 4 subintervals, but in order to desire a better approximate and to reduce the amount of white spaces being left out right here, then I can increase to, let's say, how about you see, that's a little too extreme. How about 10 subintervals? Okay, 10 subintervals, and you can count directly right here on my computer screen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have a much better. So I don't want to waste anyone's time to go over the calculation, because it's the exact same problem. Ideally, this is M10 right here, 10 subintervals, and the calculator of mine, the decimals already gave me a quick answer. So here, let me swing back to my board right here. If we are using M10, okay, M10 right there on the computer screen, as you have seen, M10 came to point, and I shouldn't say came down, it came to 0.3325. Okay, and according to the demonstration with decimals graphical illustration here, then the amount of white spaces has been squeezed out quite well right here. So we have much less, and the amount of green shaded area here is a lot closer already to the actual area. Okay, and so now let me hide away all the midpoint line right here to make the picture less confusing, and then I'm gonna make things a little more extreme. Okay, so now I'm really gonna put more subintervals in there. So right now with 10 subintervals, I'm not happy yet. So let's increase. Let's squeeze in more rectangles. So now how about 60? Okay, so M at 60. All right, so we have at this point with our own human eyes, it's already very hard to see the difference between the amount of space under the curve and the space that, the white spaces here. So we don't see much difference. And so with 60 subintervals using the using the midpoint rule, I came down to according to the calculation with decimals, M60 came out to be, so that was 0.333, okay, 43101, and a lot longer. Okay, so but in the end, none of these. So I've done a few. I started out with M4, okay, and the area was closer to 0.328125, and then I improved the precision by increasing the number of subintervals, and M came to 0.3325. And so the idea now is that designated area is even closer. It comes better to M10. Okay, so 0.3325, and this is M10. But still, that wasn't a happy answer for me yet. If I desire even better accuracy, I increase to M60 like that. And so M60 here is 0.3333, 101, and a lot longer. And area, our desired area is even much closer to this. Okay, so our actual area now is really close to the point that we can almost ignore all of that little spaces, because even I stand right next to my computer screen, I couldn't even tell the difference between in those white space, the difference from the curve down to the empty white spaces right there. Okay, and so, but none of these is the actual area that we desire. But at least here it gives us a demonstration that, again, the Riemann sum is an approximate, and it's a tool. It's a tool for us to approximate the left endpoint. To approximate the area, any area between a given function and the x-axis inside an interval from start to end, like that. Okay, and so now let's give it, just like the left endpoint rule and the right endpoint rule, let's give it a formal definition. So I am going to erase this board of mine. And then after nailing down the general definition, then I am going to give out the next example. So as a formal definition, okay, as a formal definition. And so again, just let f of x be continuous, okay, on the interval from a to b. Okay, and so, and of course, with this given interval from a to b, here is our main target of the interval right there. And so now just let me be a little more brief compared to the way how many standard calculus textbooks deliver the definition of the midpoint rule with the lengthy wordings right there. So Mn right here, the Riemann sum using midpoint rule with n subintervals inside of that interval. So what we have been doing, on each I, at each I subinterval, we choose a value x. Okay, we choose a value x that's being right in the middle. Okay, so in the end, this is a chosen value in the I subinterval, just like that, just exactly like the concept that we've been doing. Like say for the general Riemann sum, in any I subinterval, we make a chosen point, we pick a chosen point, and we obtain the height by evaluating that chosen point into the function. So we're doing the same thing here. The midpoint in any either subinterval is going to be substituted into the function to get the height, and we're going to multiply with the delta x. Okay, so now in addition, I am going to give an, and then that I will provide that clarification of the delta x a little later. But now this is the area of one rectangle over the specific ith subinterval, and now we need to sum all of those rectangle areas from the first rectangle to the nth rectangle, and that's the general definition of our Riemann sum using midpoint rule with n desired subintervals. Okay, and so now again, as an extra clarification, so delta x right here is famously calculated by the ending value of our interval minus the beginning point over n, the number of desired subintervals. Okay, and so, and then that I will provide that clarification of the this formula right here is called, okay, that formula is called, and now I'm going to write that in red ink. The midpoint. The point now is to understand what's going on, but a precise name people can call it, in a few various ways here. And I'm not guaranteeing that my way of calling that is the most standard one, but it reflects enough the idea. So it's the midpoint Riemann sum. How's that? Okay. It's the midpoint Riemann sum. Okay, and so for n subintervals, okay, to be, but that information here is just minor. So the midpoint Riemann sum, okay. How about at n subintervals? All right, so that's what m sub n is. In addition to the left endpoint or right endpoint, or now we can use midpoint. So I don't want to in the end we don't want to set into the idea of using Riemann sums forever. So I don't want to go anywhere further than the midpoint rule. So we started out with the left endpoint rule, the right endpoint rule, and we extended our idea into using the midpoint rule. It's all about getting a working approximates of the area. But now in the way how I'm seeing it, I'm going to navigate over to the other board. In the way how I'm seeing it. And the chart that we partition our midpoints for the midpoint rule is still here, but the idea now is that in a given subinterval, okay, say from 0 to 1, and we're breaking it down into the number of desired subintervals as we indicating. And so the general formula for the Riemann sum was stating that so S of n, again, is the sum of all rectangle areas from the first rectangle where each height here is a chosen point, and that's what the C here, each height here is a function value at the chosen point in a specific ith interval, multiplied with the delta x width right there. And we're summing up from the first rectangle to the last rectangle. So the chosen point, so I've been demonstrating the idea that we can choose left endpoint, okay, left endpoint on the first interval, left endpoint on the first interval, left endpoint. So that's why we call it's a rule. It's a rule so that on any subintervals we chose uniformly. I use the term uniformly just to indicate that we do the same thing for every interval. That for every interval we chose the left endpoint. That's what the left endpoint Riemann sum is. And then on the other hand, we can also in each interval we can also come up with a rule to choose the right endpoint. Okay, and then on just now we learned on each interval we can also decide to go with the midpoint, chosen point, and those are rules. But in the end, when your understanding become more advanced, we don't even have to choose midpoint. We don't even have to choose left endpoint. We don't even have to choose the right endpoint. We can choose just a point somewhere. Okay, and it doesn't even have to be a rule. We just simply pick a point in the first interval and pick another point. And pick a point in the second interval, and the point in the second interval doesn't even have to be in the same rule with the first point like that. That's what CI really means like that. It's just basically any point that we can generally pick. And so for us here being the starters, the left endpoint is making life easier, right endpoint is making life easier, and midpoint is, so anytime we can set for ourselves a rule that doesn't violate any of the work and it makes life easier for us, we stay with the rule. But don't forget that in the real true reality, we never have to set. So see, I'm demonstrating right here in my rectangle, in my subinterval number 1 right here. I chose a point that's closer to the left. My subinterval number 2, I chose a point closer to the right hand side. In my third interval, I chose a point closer to to the midpoint, okay? And then in my fourth interval, it could be right here, exactly the midpoint. So these are all chosen, and my point to emphasize is they don't even have to be these. They don't even have to be in a rule, okay? Like all left endpoints, or all right endpoints, or all midpoints. They don't even have to follow one certain rule like that. But that's for, you know, when you become more mature, and in the end, for our the beginning calculus course, but we do formal relearning to this. We definitely don't want to set the rest of the quarter into only doing the Riemann sum. And so, I only need to mention the idea, but we stop at learning about the midpoint rule, and once we finish with the midpoint rule, we are good to go. So here, the reason I mentioned, so that you can start getting comfortable with a few terminologies, that's all. So in the end, these chosen points right here that I put on my charts, many textbooks, many standard calculus textbooks refer to these as sample points. Sample points, okay? So left endpoint, as we set as a rule to go with the left endpoint, all left endpoints or sample point is a set of sample points, okay? And then all midpoints together is a set of sample points. And then in a more general case right here, any one of our chosen points. So this is C1 right here for that first point. This is C2 right here. Okay, this is C3, the chosen point in the third interval, and the chosen point in the fourth interval. Okay, so this is sort of like an irregular rule right here. Okay, but in the end, all of these C points, they are supposedly the sample points. That's the name. But to be honest, in my own personal experience over years of teaching, I never even have to use this word too oftenly. Okay, but in case you have a textbook that use this term right here, then I'm introducing that here so you won't be surprised. All right, and so now we are ready for getting into the next example, and now I'm going to specifically focus on the midpoint rule that we just now learned. All right, so let's now call that example 3 right here. Okay, and so I'm going to use a slightly different instruction right here. We want to evaluate the following. Okay, the following Riemann sum. I need to correct my spelling. Okay, so evaluate the following Riemann sums here. Okay, so part A, let's say using the midpoint rule. All right. And so in part A, our function here is given to be the x squared function, okay, over the interval from -1 to 2, -1 to 2, and with 4 subintervals, okay, with 4 subintervals. Okay, and so now I'm going to step over to the other board, and let's quickly make a sketch. So with 4 subintervals, then the beginning point of our interval is here at -1, and the ending of our interval is at 2. So halfway, 4 subintervals, because n equals 4. Okay, that's the number of subintervals. And so now that means we're looking at 0.5 is here, or 1/2 is here at our midpoint right there. Okay, and then this is going to be -0.25. Okay, and this point right here is a 0.75. 1.25 actually. All right. And we can get these in numerical value. This is a negative 1/4, this is a 1/2 here, and this is a 5/4. All right, and so of course each of our delta x is the ending point is 2 minus the beginning point is negative 1, and then divided by 4 subintervals. Okay, and so now we're looking at delta x. Each delta x equals 3/4, and that's how it's consistent with each one of these. From negative 1, with adding a 3/4 over, we have a negative 0.25, or it's just a negative 1/4, and then we keep adding up with all the 3/4 up. Okay, and so now we are ready for laying down our work here with the midpoints. But now, and actually, as far as the midpoint, so now I think it would be a better idea that so the midpoints are here. All right, so these are the midpoints. Okay. And so negative 1 plus a negative 0.25 over 2, that is a negative 0.625, or, okay, so negative, so that point right here is negative 0.625, or it's a negative 5/8. Okay, and so that point right there is going to give me a 1/8, because I'm a little bit faster with the fraction. So that midpoint of the second interval is a 1/8. Okay, and that midpoint in the third interval is a 7/8. And that last one right here, that midpoint of the fourth interval, for now, is a 13/8. All right. So that's how we sketch down all the partition, all of our sample points, or here in this case being the midpoints in each of our subintervals. Okay. And so now, so of course in that way, the symbol for midpoint rule, Riemann sum using midpoint rule with 4 subintervals, is once again M4, just like how we did that in our first activity. And so now I am going to sum. So the height of the first rectangle is going to be f at negative 5/8, and I'm multiplying that with the thickness here, the delta, the width here of the rectangle being a 3/4. And then I'm going to add to the function value at 1/8 times a 3/4. That's for area of the second rectangle. And then the third rectangle has height being the function value at 7/8, midpoint of the third subinterval, and multiply with the width, three-fourths. And now I'm adding with the area of the last rectangle, the height being determined by the function at 13/8, and multiplying that with the width, 3/4. Okay, and so now allow me to quickly use my calculator to find the final answer. All right, so for this problem, my answer for M4 is going to be 2.859375, and that could be a lot longer. And it all depends on, the rounding requirement in each of your different assignments there. So watch out for rounding requirements. Okay, but that's how we obtain M4, this Riemann sum using the midpoint rule over here on this function. in that interval with the desired 4 subintervals. And that's why I was using M4 as for that notation. All right, and so now we are ready for the next part of our current example. So now it's the same instruction. All right, so we want to evaluate the Riemann sum using the midpoint rule. Again, but how about in part B here, let's look at our function being x cubed. Okay, it's the x cubed function over the interval, how about from -1 to 0. And I'm using about 6 subintervals. 6 subintervals. Okay, and so now in this way, it's a good practice that we always create for ourselves a chart that's sketched down all of our sample points and along with all the partition points. Okay, so here's our chart. -1 and 0 is here. Okay, now we want 6 subintervals, and so delta x, now the width of each of our subintervals has to be 0 is the ending point minus -1, and we divide it by 6. So delta x here is going to be a positive 1/6. So delta x is always a positive value. Okay, and so now as far as the picture, halfway is here, but we're breaking that into 6 subintervals. So each of the half interval here is going to be broken down into 3 further subintervals. Okay, so those are the one I'm looking at. Yeah. All right, and so now as far as partition points, this first one right here is a -1/6. Okay, and then -2/6, which is a -1/3. Okay, and so these are the partition points to break our interval into partitions. And then this is -3/6, which is a -1/2. Okay, and then about here, -2/3 and -5/6, and these are the partition points. Okay, and then we specifically want all of these midpoints. So we want midpoint in each of our interval, and that's the whole intention of this particular problem so far. So these are the midpoints. So the first midpoint here is a it's just easier for me to go from, because we're starting out with 0 here, even though it's on the right hand point. So it's just a little bit of experience, even though of course we always read from the right to from the left to the right. But here, the way how the numbers are, and it's easier for me at least. So I'm sharing that experience with anyone. So -112 is the first one from the right hand point, and then back further. Okay, and then now each one is a space of 112. And so now here in that, then minus 1/4 is here. Okay, and then -5/12 is here. Okay, and then that's our halfway point of the interval. And then here, actually I mean here, -7/12. Okay, -3/4, -11/12 like that. All right, so those are our our sample points being the midpoints. So -112, let's use right arrow to indicate those are the midpoints. Midpoints here. Okay, midpoint, this is a midpoint, this is a midpoint. Okay, and this is the midpoint. So we got 1, 2, 3, 4, 5, and 6 midpoints. Okay, so now we are ready for getting into the calculation. So back on my beginning board again. So with the actual calculation, so now I have to call that. So it's a midpoint rule, I mean Riemann sum with the midpoint rule using midpoints in each subintervals, each of the subintervals. And so here M6. So first subintervals, now we're going to actually have to count, we're going to actually have to accumulate from the left to the right, even though when I lay down all of these, it's easier for me, it was easier to go from the right to back because we actually have a start here at 0. We had the ending point, I meant at 0, and then so it's easier to start with 0 and going further negative. But now really when we're accumulating up the areas, then we're going from the left to the right. So the first midpoint here is at negative 11 over 12. Like that. Okay, and so go ahead and observe that chart closely. And now we're looking at function, the height of the rectangle is the function value at negative 11 over 12, and I'm multiplying that there with the width 1/6. And I believe that 1/6 delta x is on the other board, it's right here. Okay, and so multiply with 1/6. And now we're moving on to second subinterval. And so that gives me the height on that second subinterval is the function value at negative 3/4. That's the height, and then multiplying with 1/6, the space right there, plus, and now the next one, I mean the third one is at negative 7/12 times 1/6 for the width, and then that's the third interval. The fourth interval now is going to be the function value at negative 5/12, okay, and multiply with 1/6. Okay, so 1, 2, 3, 4 subintervals so far. And so now the next one now, fifth one is going, the height of the rectangle there is going to be the function value at negative 1/4. Okay, and then multiply that height with 1/6. And the last one of our interval, the functions, I mean the interval height, the rectangle's height is going to be the function value at negative 1/12 times, and then that height multiplied with the width 1/6 right here. Okay, and so now again I am going to quickly step out, and so of course needless to say these are negative 11 cubed times 1/6 in the next step, but I'm running out of space here, so allow me to not write down that stuff, and anyone viewing this video should be fluent enough to understand, and I also skipped that step to lay down the calculation step when we plug these values into the function, even in the earlier problem like that. But now I'm going to step away and get that calculation done with my computer screen right there. I mean with my calculator on the computer. All right, so now my answer is now ready for the hopefully something not too shocking. Negative, okay, negative 0.24652. And actually after that too, it's 7 and a lot longer. Okay, and so my M6 in this problem is a negative 0.24657 and a lot longer. Okay, but if anyone is a bit worried about negative answer, again, roll back to the earlier part of my explanation earlier before this part of this lecture. But I never said that Riemann sum is necessarily an area. Riemann sum is just a Riemann sum that we. So on my other board, the idea of the Riemann sum, again, I have to emphasize the Riemann sum only needs to be, it's a sum of the function value at any I subinterval. So that's what this f of c sub I multiply with the delta x right here. So anytime we perform this operation, summing up all of the height of the function times width, height of the function times width, and summing that up from the first subintervals to the last nth subinterval, we have a Riemann sum. And so that does not necessarily mean it has to always be positive, because now let me bring up the actual picture. So on the computer screen right here, this is the red curve is our x cubed function. The interval is from 0 to 1. Okay, the interval is from 0 to 1, and with the midpoint rule, that's how we created. That's how we created all of these green rectangles right here. So again, that red curve is the x cubed, but the interval is from negative 1 to 1. I mean negative 1 to 0. And then we broke that down into 6 subintervals. And you can quickly count right here, 1, 2, 3, 4, 5, and 6 subintervals. But this times all of, according to the way how our interval is, and according to the way how the Riemann sum is being performed, is being done, then the height of the function of the height of each rectangle must be, and that is because of the way how the function is. The function is a negative value. The function has negative value when it's in this interval, anywhere from -1 to 0. And that's why any one of our rectangle has a negative height, or in other words, graphically speaking, it's a height that points down. Okay, and so that's why summing up all of these negative heights, okay, it gives us a final answer being a negative answer, just like how we have seen it here. Okay, and so that hopefully that explains and that reinforces again the understanding that the answer coming out of a Riemann sum is not necessarily an area, but it's as I have explained earlier, it's a tool. The Riemann sum is a tool perfectly good for us to approximate the area. Okay, but in the end, the Riemann sum is not an area. Okay, the Riemann sum just will never be an area. Okay. All right, so this example right here concludes our lecture about the idea of using the Riemann sum to approximate an area right here. And in this problem in particular, I purposely did not say that it's an area problem. We just want to particularly focus on our skills of learning how to operate with the Riemann sum using the midpoint rule right here with various different subintervals, the number of desired subintervals.